Here's the text with proper punctuation. Pluto is a remote and confounding midget planet that was once a piece of our solar system's planetary gathering. However, later astonishing declarations by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a frightening revelation. They suggested that this cold world is on a potential crash course with Neptune. But how could this happen, and what might be the repercussions of such a gigantic event? Are we seeing an intriguing cosmic phenomenon? Or is there something else to this approaching grandiose conflict? Join us as we examine the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was renamed a dwarf planet in part due to its strange orbit, remains a subject of interest and exploration in the astronomical community. According to recent figures by leading scientists, Pluto's orbit is dangerously close to Neptune's, with both Neil deGrasse Tyson and Michio Kaku sounding the alarm about a potential dangerous collision between these two planets that could pose a significant threat to Earth. How is such an event even possible? Pluto's orbit around the Sun is unlike any other planet in our solar system. It requires a surprising 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution. But the interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, straying greatly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For around 20 years in each orbit, Pluto actually draws nearer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This prompts the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique path. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit, despite these complexities, is evidence of the intricate nature of space mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how the paths of Neptune and the Sun's gravity all interact in a complex way. The terms libration and scope libration, along with the VZK oscillation, are essential to this puzzle. According to astrophysicists, what's keeping all planets in their orbits is a libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's located at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from igniting. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's positioned well above their orbital plane, providing an additional layer of security from potential collisions. Another crucial factor in this equation is the VZK oscillation, named after three scientists, von Zeipel, Kai, and LV, who studied how things move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the VZK oscillation helps us understand why its path around the Sun is so unusual. Although Pluto's path seems erratic, this oscillation helps keep it moving smoothly for long periods. The VZK oscillation shows that even when things in space seem wild and random, certain patterns and rules keep everything in order. These factors help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or go off course. This three-body problem helps us understand how these factors change based on how these space objects pull on each other. Studying this helps us learn about Pluto, our solar system, distant worlds, and their stars. Mathematical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is indeed chaotic. minor deviations in initial conditions lead to massive differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over extremely long timescales, effectively keeping the chaos at bay. Recent computer tests have helped us grasp how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's path around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's path stable. However, Neptune isn't the only one helping. Jupiter's gravity also plays a significant role in keeping Pluto's orbit safe and stable, with Saturn contributing as well. Altogether, these tests show that Jupiter's gravity alone is enough to ensure Pluto remains on a stable path for a very long time, even billions of years. It's as if Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without encountering trouble. These phenomena are essential in the context of the universe for maintaining the order and consistency of space bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a ripple effect on other celestial bodies. For Pluto, particularly with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. This provides a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to better grasp our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is clearly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computer simulations has been incredibly helpful for scientists to figure out how Pluto moves in space. These simulations use complex math to recreate how Pluto and other space objects, like Neptune, pull on each other. By changing small details in the simulations, astronomers can see how even minor changes can make a big difference in where Pluto ends up. In the late 1980s, these simulations revealed something truly fascinating about Pluto's path. Even though it has factors like libration and scope libration to keep it stable, its orbit can still be very wild and unpredictable. If you start with just a tiny difference in where Pluto is or how fast it's moving, over many years its path can end up looking very different. But even with this chaos, Pluto's orbit remains stable for an incredibly long time, like billions of years. This means Pluto's journey around the Sun has a sort of order to it, even though it seems chaotic at first. Predicting cosmic events, especially when they involve chaotic orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. While numerical simulations provide a powerful means to understand and anticipate the future paths of celestial bodies, they also highlight the limitations in our predictive abilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any minor error or misrepresentation can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits, like Pluto's, reminds us of the ever-evolving and dynamic nature of the universe. While we have made great strides in understanding space, the case of Pluto reminds us that our knowledge of the universe still remains limited. Grasping the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So why are prominent astrophysicists only now raising concerns about a possible collision between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in popularizing astronomy, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's stance on Pluto's reclassification is rooted in the ever-expanding knowledge of our solar system. He views the reclassification not as a demotion, but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits, like Pluto's, as a reminder of how much there is still to discover in space. The fascination with these mysteries, particularly the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our solar system. His thoughts challenge us to keep questioning and exploring the universe, embracing the unknown as a crucial part of scientific discovery. Meanwhile, Michio Kaku, a renowned theoretical physicist, delves into the enigmatic aspects of space exploration and the future possibilities of our universe, emphasizing the intricate dynamics of celestial bodies like Pluto and Neptune. Kaku's approach to the potential collision between Pluto and Neptune is informed by his deep understanding of the three-body problem and the chaotic nature of orbital mechanics. He suggests that while current models and simulations indicate a stable system, the inherent unpredictability of chaos theory means that we can never fully rule out the possibility of a cosmic event. Kaku's views emphasize the importance of continued observation and the development of more advanced simulations to better understand the long-term behavior of celestial bodies. Kaku also connects these cosmic phenomena to broader questions about the future of humanity's exploration of space. He envisions a time when our understanding of these dynamics could inform not just our study of distant worlds, but also the development of technologies to navigate and possibly mitigate the risks posed by such cosmic events. Kaku's insights underscore the need for a multidisciplinary approach to space exploration, blending physics, astronomy, and technology to unravel the mysteries of our solar system. He encourages us to think about the future of space travel and our place in the cosmos, reminding us that the answers to these mysteries could shape the destiny of humanity itself. Neil deGrasse Tyson and Michio Kaku's perspectives serve as a compelling reminder of the complexities and uncertainties inherent in our understanding of the universe. Their insights into the potential collision between Pluto and Neptune challenge us to reconsider what we know about our solar system and to remain vigilant in our quest for knowledge, as the answers to these cosmic mysteries may have profound implications for our future. As we continue to explore the vastness of space, Tyson and Kaku's contributions to the field of astrophysics inspire us to embrace the unknown and to push the boundaries of what we understand about the cosmos.